All right, so the question is whether or not these two integral expressions are equal. The reason why we might think that they are is because the integrand is even, and here x goes from -2 to 2, and here I'm doing 2 times an integral where x goes from 0 to 2. Okay? That's why we might say that they are the same. On the other hand, we have at no time in this process sketched a graph of the region of integration. So what we should begin by doing is sketching that region to see if it is symmetric. Remember, the integrand being symmetric is not good enough. Okay? We need the region to be symmetric as well. X is going from -2 to +2, and at a constant value of x, y is going from x squared, which looks like this, actually, up to 6 plus x. All right, what does 6 plus x look like? Well, when x equals -2, 6 plus x will be 4, which coincides exactly with this graph. When x equals 2, 6 plus x equals 8, which is twice as far up. All right? So our region looks like this. Okay? This here is y equals 6 plus x. All right? And notice that it is not symmetric. The right-hand side is not just a mirror image of the left-hand side. Okay? In fact, we would expect that the contribution from the right-hand side is significantly larger than the contribution from the left-hand side. I mean, not just a little bit, because we've got this whole extra region up here. Okay, and we're adding up x squared. So we would expect this side of the equation, where we're doing twice the positive x contributions, to be larger than this side. Okay? So in fact, these two things are not equal. The region doesn't have symmetry, so it doesn't matter whether or not the integrand is even in x. We will not have symmetry for the integration. Okay? Now, before I end this problem, I want to go ahead and show how we would reverse the order of integration, because this is a particularly tricky region as far as that's concerned. The book would refer to this region as a type 1 region. And that's because if I integrate y at a constant value of x, as we're doing here, I'm going to get rid of this one. I can write it as a single integral. But if I try to integrate x at a constant value of y, I run into a little difficulty. When y is smaller than 4, x is going to go from the left side of the parabola to the right side of the parabola. But at larger values of y, x goes from the line to the line, okay? From the diagonal line to the vertical line. So that means if I'm going to try to send y out first, I have to split it up into two integrals. One that takes place when y is less than 4, the other that takes place when y is greater than 4. So let's see how we'll do that. At a constant value of y that is less than 4, x goes from the left side of the parabola, which is negative the square root of y, to the right side of the parabola, which is positive the square root of y. On the right-hand, or sorry, when y is above 4, x is going to go from the diagonal line to the vertical line. So I'll go from 4 to 8. X will go from here, where it's y minus 6, up to the vertical line, where x is 2. Okay? And that would be our integration. Okay? It's not possible to write it in this order as a single double integral, at least not in any straightforward way.